Hello, this is Team 6, and we're going to talk to you about the maze runners. I am Ben Sperker.
I'm Steffa Falvey.
And I'm Bowie Zhao.
The goals of this project include designing and building a maze-solving rover that will communicate the path to the finish line from the lead rover to the following rover. We will develop a communication protocol that the central server, a Raspberry Pi, will use to route messages.
Our project contains 2 rovers and a server. Both the rovers, the lead rover and the following rover, begin at the start line just behind the tape. When a message is sent to the lead rover will begin and autonomously go through the entire maze before finishing at the finish line, which it knows because it is bounded by the black tape. Once the lead rover finishes the maze, it sends a start message to the Pi, which then tells the following rover to begin the maze as well. But this time, the following rover at every intersection will stop and ask for the direction from the server, which it will then receive from the lead rover. This way, the following rover will complete the maze in the shortest paths possible.
On the left, we see what our final maze looks like. On the right, we see what a valid intersection looks like.
The lead rover starts at the beginning of the maze. When it reaches an intersection, it will mark down all available paths, and the algorithm will make a decision on which way to proceed. When the lead rover reaches the finish line, the quickest path to the finish line is stored. This algorithm is quite robust and dynamic since it only stores intersection information. This algorithm could work on any size maze.
Now we're going to go through an example of the algorithm. First of all, we have an array storing north, east, south, and west values, ideally as a linked list for each cardinal direction.
Beginning at the start, we move north, and at our first intersection, we see nothing to our north, an unexplored area to our east, a dead end to our south, and more unexplored area to our west. The algorithm works in such a way which north is the first direction tried, east is next, then south, then west. So at this first intersection, since we don't have a north, but we only have an east and a west, we first go down the east path. So we mark the east as the current direction. When we reach the second intersection, we mark the west as available since we could still go west on that first intersection. At the second intersection, we see we can go north or east, and since the algorithm defaults going north, we go north. Then we realize we're at a dead end, so we need to turn around and go back to the second intersection. Getting back to the second intersection, we must mark that previous path as a dead end, and now look to go west, our only unexplored path. We now head east, and we realize we've reached the finish line, so we mark that east path, found it. Having found our destination, we now go through the other elements in the list and mark all current paths as the destination. This will allow us to then read through and find the correct path. When asked by the following rover, the lead rover will reply right at the first intersection, right at the second intersection, and there you have it.
The follower rover begins moving from the start of the maze once the lead rover has reached the finish line. When the follower rover detects that it is at an intersection, it will send a direction request message to the lead rover that includes a sequence number for the current intersection. The lead rover responds with a message indicating which direction to turn at the intersection, left or right. The follower rover then sends a message to its motors that signals which way to turn, and it turns in the specified direction. This process is repeated at every intersection until the follower rover reaches the end of the maze, marked by a solid black area. This flowchart explains the control process for the follower rover. When the rover arrives at an intersection, it first asks for a direction. Then there is a short delay when the rover is checking for a response message from the lead rover. If the follower has checked more than 5 times for a response and receives no response, the follower rover sends another direction request for this intersection. If a response is received within 5 checks, the follower checks the validity of the response. If the response is not valid, the rover returns to the short delay. If the response is valid, the intersection number is checked. If it is not the correct intersection, the rover returns to the short delay. If the message is for the right intersection, the follower attempts to send the message to the motor thread. If the sending is successful, the rover will then check to see if it is at the end of the maze. If so, the rover stops, otherwise the rover turns in the specified direction.
The Raspberry Pi was set up as a Wi-Fi hotspot using a Raspbian operating system and a USB Wi-Fi attachment. A Python socket server script was run on the Raspberry Pi. This script utilized client sockets on ports 2000 and 2001. The follower rover was equipped with a Wi-Fi module that connected to port 2001, and the lead rover was equipped with a Wi-Fi that connected to port 2000. Using the socket select function in Python, we were able to wait for socket input and output efficiently. The select function enables easy, simultaneous monitoring of multiple connections.
The Raspberry Pi has multiple functions as the main server. The Raspberry Pi reassembles split incoming messages before passing those messages to the correct destination. In addition, the start and end flag and checksum of each received message is checked. If any of these fields are invalid, the message is ignored and an error is printed to the terminal. All messages received and errors encountered are also printed. As explained previously, a dedicated client socket is used for each rover to easily identify where a message is coming from. In addition, if the socket experiences a connection error or fails to receive messages in a reasonable amount of time, the sockets are closed and restarted. The overall communication model uses the Raspberry Pi as a router that is responsible for passing messages to and from each rover. This router ensures that all messages arrive at the correct destination, given the message type and source. Extensive testing was done on this communication system to ensure its reliability and robustness. The server was run overnight multiple times with simulated direction responses and motor commands. During these runs, the intersection number and 8-bit value correctly incremented from 1 to 255. It was incremented when a direction request and direction response were successfully sent and received for each intersection. The server was tested using simulated lead rover code and actual follower rover code. The lead and follower code were flashed to 2 separate PIC boards, which confirmed that the system would work for the final implementation on 2 separate rovers. Loss of Wi-Fi connection was simulated by unplugging a Wi-Fi module mid-run. The server immediately stopped and restarted seconds after the Wi-Fi was plugged back in. This test made sure that the system restarted when Wi-Fi communication went down on one or more Wi-Fi modules. The system restarted on the correct intersection, specifically the intersection that the rover lost connection on, which proved the system's robustness.
A primary feature that both the rovers have is the ability to use their motors with multiple PWM states for PID line following. We utilized the chip kit motor shield and the output compare signals so that we could move the motors in different directions such as forward and backwards to do 90-degree rover turns and also 0-degree turns where one wheel is going forward and one was going backwards. This was crucial to our design such that we can follow the line accurately and turn at right angles and follow the line and continue to the end of the maze. The second sensor that we used that was analogous to both rovers was the 8-channel analog Pololo IR sensor. This was used and mounted on the bottom of each rover seen in the bottom right corner in the center position such that we can track the lines and detect intersections exactly when they happen. Out of the 8 sensors, we were only using 5 of them, so that we could have an equal amount of sensors where we had one in the center and two on each opposing sides. On the PIC boards, we used and set up the PIC to use 10 samples per interrupt for greater precision, such that each IR sensor could have 2 samples per interrupt, which would then be averaged. Overall, these sensors would be used for line detection, line following, and intersection detection, which was crucial for the completion of our game. The rovers, as you see in this picture, were designed such that they would meet the design requirements that our project required. We had the base rover with the motors such that they can turn in different directions. The IR sensors mounted at the very bottom such that we can detect intersections and the lines accordingly. And the Wi-Fi is mounted on the top with an LED array, you can see in brown, that is mounted to show when the line is being detected. These components, being featured on both the lead and follow rover, were required such that we can complete the mission and show how design meets implementation. This is a video demonstration of our lead rover going through part of the maze autonomously. When it reaches the first intersection, it performs an autonomous turn to the right, following the algorithm. And now it's line following and moving to the second intersection before it intercepts it. Once it reaches the second intersection, it will then use the algorithm to determine it will turn left. The white line you see at the top is our current final destination, where it will stop due to time constraints. So once it reaches it, it will stop, and it technically finished the map. Thus, this was a key item in mind while we were designing the rovers. For the servers, it was made sure of that these Wi-Fis would be connected as unique elements such that the server would be able to distinguish between the lead and follow rover and also be able to reconnect autonomously when signals were dropped, missing, or if packages were split, messed up, or just not coming. These were done and tested such that we could be certain that the rovers were receiving the correct messages and at the moments that we wanted them to. Next, we also accounted for line following through PID by making sure that if during turns or when the rover was making its movers move too much, that it will adjust accordingly such that it will not overshoot the line and be able to continue following it. These, along with the rover states on when it sees blank spaces or when we picked it up, make sure that the rover's wheels might stop turning at a certain state such that it would not completely keep on moving or fall off a table. Also, at the beginning of our game, the rover start behind the line in an initial position, and it will not start moving until we give the go command. These designs were tested in a multitude of design environments and situations, such as when a lot of teams were verifying in the lab all at once with all of their Wi-Fi's, and we were sure that our Wi-Fi's did not have any problems receiving or sending, and that is true. The rovers were also able to continue working even after the fire alarm systems went off twice before validation nights, showing just how robust our design really was. Finally, I'd like to talk about some design improvements we wanted to do with our rovers. Initially, we wanted to put 2 of the same IR sensors, which were the analog Pololus, on each rover such that there would be one in the center, as we already have and seen, and also one in the front. But due to constraints of what the TAs were provided, we're only able to have 2 sensors in total, such that we were not able to mount 4 completed, but only 1 on each rover for 2 total. The additional sensors would have aided us in much better line following and intersection detection. And what those sensors would have also been able to help us with is 4-way intersection. At the moment, we can detect 2- and 3-way intersections, but are unable to detect 4-way intersections such that you would see in the plus symbol. This is due to the fact that our rover is currently has its sensors mounted directly in its center, such that it will not be able to tell if there's another intersection right in front of it. Lastly, due to the different sizes and weights of our rovers, even though they have the same materials, the chassis were made such that the center of gravity and weight were different. This made it such that the turning required careful tuning for each rover as opposed to having it being analogous to both. Meaning if we were to design it again, we would have to have a modular chassis design such that our code would be able to run and turn both rovers without modifications to both of them separately. Overall, in the end, our project and time embedded allowed us to work in teams on a rover and implement it following a design. We used real-time logic analyzers, the MPLAB IDE, third-party sensor arrays, and of course wireless communication on our projects and increased our knowledge on said topics. We all learned quite a lot this semester, both technically and in regards to working on a team to get a large project done.